Clarion-Clipperton Zone, in the 1960s, scientists went out there and took images of the seafloor and said, oh my goodness, there's all of these trillions of little nodules sitting on the seabed.
Mining companies have been testing technologies to essentially suck up and retrieve these nodules and claim the environmental risks are limited.
5,000 meters below the Pacific Ocean, in a place where no sunlight has ever reached and the pressure can crush solid steel, an AI drone just found something that shouldn't exist. It wasn't a creature, it wasn't a wreck. It was something so strange that the drone, in the middle of its mission, simply stopped moving. It hovered above one specific patch of dark seafloor and refused to leave. On the surface, the scientists watching the feed went quiet, because what the drone was staring at wasn't supposed to be down there. And once they realized what it really was, none of them could explain it.
The twilight zone is essentially an area that's below the limits of normal recreational scuba diving technology, but above where you would send an ROV or a submersible of some sort.
The silent depths. The Pacific is the largest ocean on Earth, larger than every continent combined, and most of it is still a mystery. Hidden inside it is a region called the Clarion-Clipperton Zone. It sits between Hawaii and Mexico and spreads across roughly 4.5 million square kilometers. That is larger than most countries on the planet, and yet it remains one of the least explored places on Earth. As you sink, the world changes fast. By 5,000 meters down, the pressure is strong enough to crush almost any material that has not been specifically engineered to survive it. The temperature drops to nearly freezing, and the light disappears completely. Not the way it disappears at night. Sunlight from the surface gives up after a few hundred meters. Beyond that, there is no glow, no shimmer, nothing. It's a vast area, almost as big as the continental landmass of the USA. It lies between Mexico and Hawaii in the middle of the Pacific. The seafloor there is cold. It's dark, just absolute black in every direction all the time. Here is the part that gets unsettling. Humans cannot reach these depths. Even the most advanced submarines struggle to handle the cold and the crushing weight of the water above. Most missions rely on machines controlled remotely from the surface, tied to ships through long cables that feed them power and instructions. If something unexpected happens down there, scientists on the surface have only seconds to react, and most of the time, they cannot react at all. For decades, experts assumed this part of the ocean was mostly inactive, quiet, predictable, a flat plain of mud, and a few scattered creatures. But here is the catch. The Clarion-Clipperton Zone is not empty. It is paved, across millions of square kilometers, with strange dark stones. And those stones are about to change everything we thought we knew about our own planet. The AI mission. The stones are called polymetallic nodules. They look like lumps of charcoal scattered across the seafloor, and they have been sitting down there, mostly ignored by science, for a very long time. The seafloor has these amazing, weird polymetallic nodules, these mineral nodules sitting on the seabed. There is also life there. There is biology there as well. What put them on the map was not biology, it was money. The nodules are packed with cobalt, nickel, copper, and manganese, the same metals that go into electric vehicle batteries, smartphones, wind turbines, and solar grids. Suddenly, this forgotten patch of ocean floor looked like the most valuable real estate on Earth. But before anyone could mine it, scientists faced a problem. Their tools were not good enough, the cables were too short, the robots were too slow, signals took too long to travel. At 5,000 meters, even a small delay can ruin everything. If a strange object drifts past the camera, by the time the operator on the surface sees it and sends a command, the moment is gone. The deep ocean does not wait for instructions. So they built something else. Not a tool, a system. Something that could think for itself. What they built was an autonomous AI drone, and it was unlike anything that had ever been sent into the deep before. It did not need a cable. It did not wait for orders. It carried its own power, its own sensors, and its own brain. Engineers trained it on thousands of hours of deep sea footage, geological surveys, and biological data. They fed it images of every known deep sea creature, every common rock formation, every type of sediment, pattern, every kind of underwater terrain that humans had ever recorded. And here is the part that matters most. The drone had been taught what normal looked like. Pages and pages of normal, hours of normal. Every shape it might encounter on the ocean floor, the system had a reference for. That meant when it eventually saw something that did not fit, it would know. It would not need a human to tell it. It would simply notice on its own that the world in front of it did not match the world it had been taught to expect. The mission was a joint research effort across 3 continents. The central scientist on the project was Dr. Andrew Sweetman, a deep-sea ecologist with the Scottish Association for Marine Science in Oban, Scotland. Sweetman had spent more than a decade studying the seafloor of the Clarion-Clipperton Zone. He was, by his own admission, not expecting drama. The plan on paper sounded almost boring. Map the seafloor, catalog the nodules, document the wildlife, bring back useful information. But the team called this the first truly autonomous deep ocean intelligence mission, and that label was not marketing. The drone could choose where to go. It could choose where to stop. It could choose what was worth a second look. It did not follow a fixed route. It explored. Here is the part that gets interesting. A human operator watching this same mission through a cable from the surface would almost certainly have missed what came next. The signal that stopped the drone was too faint. The shift in pattern was too subtle. By the time a person on the ship had noticed something on the screen and sent a command, the moment would have been gone. The reason any of this discovery exists is that for the first time, the machine on the bottom of the ocean was paying attention faster than the humans ever could. When the mission began, everything looked normal.
We developed that technology and the skill within the academy in order to be able to do exploration diving in that region.
The drone glided over the seafloor and recorded exactly what scientists expected. Rocky sediment, scattered metallic nodules, the occasional ghostly creature drifting through the dark. The data flowing back to Sweetman's team looked routine, and the room relaxed. Whatever this drone was about to find, it seemed like it was going to be ordinary. It was not. Quick pause. Before the drone does the thing that stopped this entire mission cold. If you are pulled in this far, do me a favor and hit the like button. It is a small thing, but it tells me you want more deep ocean stories like this one, and I will keep digging them up. All right, back to the seafloor. First signal. The drone kept moving. Slowly, methodically, it crossed the floor of the Clarion-Clipperton Zone, doing exactly what it had been built to do. The cameras rolled, the sensors pulsed, the data streamed up to the ship far above. Rocks, sediment, a few small creatures, nothing out of the ordinary. But the drone was not just recording, it was thinking. Every image, every reading, every sound was being compared against the millions of data points it had been trained on. And somewhere along that quiet patch of sea floor, the comparisons stopped matching. A signal came through. It was faint, almost nothing. The kind of reading any human operator would have dismissed as background noise. But the drone did not dismiss it. It paused, it turned, and it moved toward the source. Then it stopped completely. It did not crash. It did not lose power. It did not signal an error. It simply hovered, motionless, above one specific patch of the ocean floor. The area was small, maybe 30 meters across, and it looked no different from anything around it. Same rocks, same nodules, same featureless dark mud. But the drone refused to leave. Here is the part that gets unsettling. The drone repeated itself. It would hover, focus its sensors, shift slightly to one side, and scan again. Then it would do the exact same thing all over again. Stop, focus, adjust, stop, focus, adjust. To the people watching the feed in Oban, it looked like a machine that was trying to confirm something it could not quite believe. For a while, the surface team did not even notice the strange behavior because the drone never raised an alarm. It was not in distress. It was not malfunctioning. It was just being careful. And what its sensors had picked up was a steady, faint electrical signal rising from the sea floor itself. The first instinct on the ship was to assume the equipment was broken. The deep ocean is brutal on machines. Pressure can warp instruments. Cold can interfere with electronics. Salt water can corrode anything sensitive. So the team waited. They watched the data. They cross-checked one sensor against another. They ran the readings through every diagnostic the drone had on board, and every check came back with the same answer. The signal was real. The sea floor was producing electricity. Here is the part that gets unsettling. There were no cables down there, no volcanic vents in that exact spot. No life forms known to generate measurable current at that scale. The bottom of the ocean, in complete darkness, in freezing water, under crushing pressure, was somehow making power. Sweetman's first reaction, by his own account, was to assume one of the sensors had drifted. He sent the team back through the calibration logs. They came back clean. He had them rerun the readings on a different drone pass. Same answer. The signal was not a glitch. The seafloor was somehow electrified, and once Sweetman's team accepted that, a much harder question took its place. If the seafloor was producing electricity, what was it powering? Dark oxygen. The team turned every instrument they had on those polymetallic nodules. For decades, the nodules had been studied for what they contained, never for what they did. They were full of cobalt and nickel and copper and manganese, and that was the end of the conversation. Nobody had thought to ask whether they were active in any sense. They were rocks, but under the pressure of the deep ocean, surrounded by salt water, the metallic surfaces of these nodules turned out to be doing something quietly remarkable. They were generating tiny electrical currents. Not enough to power a machine, not enough to light a bulb, but enough to be measured, enough to be steady, enough to be continuous. And get this, when the scientists followed that current through the chemistry of the surrounding water, they realized what it was capable of doing. Water is made of hydrogen and oxygen locked together. Under normal conditions, those two elements stay bonded. But if you apply enough energy, even a tiny amount, you can pull them apart. The electrical current coming off the nodules was just enough to do exactly that. Slowly, constantly, the seafloor was splitting water into its building blocks, and one of those building blocks was oxygen. Sweetman would later describe the moment the data came back. He was at his desk in Oban, late afternoon, gray light coming through the window. He stared at the readings, then stared again. He pushed his chair back from the screen and called a colleague over without saying what for. For a long moment, neither of them spoke. They just looked at the numbers. Sweetman had run the experiment expecting to confirm a baseline. Instead, the seafloor was showing him something he had spent his career being told was impossible. His first thought, he later admitted, was that the sensors were broken. He had the team rerun the measurements, then run them again with different equipment, then send a fresh batch of nodules to a separate laboratory for an independent test. Every time, the answer came back the same. Rocks were making oxygen. Oxygen at 5,000 meters down, where no light is ever touched, where there are no plants, no algae, no photosynthesis of any kind. Everything science had ever taught about how oxygen is produced on Earth depended on sunlight. Every textbook, every model, every assumption Sweetman had built his career around, and here was oxygen being made in absolute darkness by stones. Here is what makes this insane. Life beyond Earth might not need a sun. It might just need the right rocks. That single thought traveled fast out of the ocean and into the offices of astrobiologists who had spent their careers asking whether the hidden oceans of other worlds could possibly support anything alive. One of those astrobiologists was Dr. Kevin Hand at NASA's Jet Propulsion Laboratory in Pasadena, California, a leading expert on Europa, Jupiter's icy moon. Europa has an enormous ocean hidden beneath a thick shell of ice, twice the volume of all the oceans on Earth combined. No sunlight reaches it. The ice on top is miles thick. For years, the central question about Europa has been whether life could possibly survive in a place that dark and cold. When the dark oxygen results crossed Hand's desk, he later said he read the paper twice before he believed it. Conditions that had been written off as too hostile for life now matched almost exactly conditions that, on Earth, were quietly producing oxygen on their own. Europa has the metals. Europa has the water. Europa has the pressure. The argument for empty had been built on the assumption that nothing could make oxygen down there. Now that assumption was gone, and the search for life beyond Earth quietly tilted in a direction it had never tilted before. The team gave the phenomenon a name: They called it dark oxygen. Oxygen produced without sunlight, without biology, without any of the processes we thought were required. A purely geochemical reaction happening in a place where nobody had ever thought to look. By every rule of biology Sweetman had been taught, it shouldn't exist. But there it was, being measured in real time on a screen in Scotland, and the drone was not done. While the team in Oban was still processing what the dark oxygen data meant, the machine kept moving. It crossed onto a new stretch of seafloor, and what it picked up next was harder to explain than oxygen. Moving patterns. The drone's mapping sensors had picked up formations on the ocean floor that did not look right. They were not the rough, irregular patterns that erosion and sediment usually leave behind. They were too regular, too organized. There were spirals, grid-like arrangements, repeating ridges that lined up with each other in ways that natural geology rarely produces. The AI had been trained on thousands of hours of footage of natural deep-sea formations. It knew what currents do. It knew what tectonic activity does. It knew what a slow rain of sediment over millions of years looks like. These shapes did not match any of that. The system kept flagging them over and over, and that repetition forced the human team to take a closer look. Here is the part that gets unsettling. The scientists pulled the footage apart frame by frame. They compared the patterns to known geological formations. They ran them through models of erosion, current flow, and biological activity. Nothing fit. The shapes looked stable, almost intentional, as if something had organized them. But it was the next observation that turned the room cold. The patterns were moving. The motion was tiny. It was the kind of change you would never catch with the naked eye. The kind of shift that only becomes visible when you compare data from one timestamp against data from another. But it was there. Some ridges had extended slightly. Some spirals had tightened. The seafloor was rearranging itself. That should not have been possible. Changes like that usually come from tectonic activity, from underwater currents, from external pressure of some kind. The drone's sensors had been watching for all of those, and none were showing up. There were no shifting plates in that region. There were no strong currents. The water around the formations was almost completely still. Whatever was moving the seafloor was coming from inside the system itself. And get this, when the team checked the electromagnetic readings the drone had recorded during the same period, they found the next layer. Tiny fluctuations in the local magnetic field had appeared at exactly the same moments as the structural shifts. The two were synchronized. Whatever was happening down there was tying together energy and physical movement in a way that did not match any model anyone had brought to the mission. Here is the part that gets unsettling. The synchronization was clean, it was not a coincidence, and it was not random. The same rhythm the seafloor was using to rearrange itself was the same rhythm the local magnetic field was pulsing at. To the engineers in the room, it looked less like geology and more like a circuit, a natural one, a circuit that had been running undisturbed on the floor of the Pacific for a very long time. Some researchers stopped calling what they were seeing a discovery and started calling it a system. Something stable, something continuous, something that had been quietly running for thousands, maybe millions of years, hidden under 5 kilometers of black water with no one watching. By every model the team trusted, it shouldn't exist, but there it was, organizing itself on the seafloor on camera. And here is the catch. A system that has been running undisturbed for that long is not strong. It is balanced. Pull one piece out and the whole thing might never recover. Sweetman knew exactly what was sitting at the center of that balance. He also knew exactly who was getting ready to drag industrial machines across it. The bigger threat. The same polymetallic nodules that produce dark oxygen, the same nodules that seem to be tied into whatever larger system the drone uncovered, are also the main target of deep-sea mining. They have been for years. Companies all over the world have been preparing for the moment they get the green light to send industrial machines down to the Clarion-Clipperton Zone and start scooping up the seafloor. The reason is simple. Those nodules are full of the metals that modern civilization runs on: cobalt, nickel, copper, manganese. The same metals that go into electric vehicle batteries, smartphones, wind turbines, and solar grids. As the world races to build out clean energy, demand for these metals has exploded, and the nodules sitting on the deep ocean floor look like one of the largest untapped reserves on the planet. For most of that planning, the nodules were treated as nothing more than rocks, dead, simple, scattered, just sitting there waiting to be collected. That is how the entire deep sea mining industry was framed. Pick up the rocks, process them, power the future. But the drone changed that picture completely. Here is the catch. If the nodules are the source of dark oxygen, then removing them does not just remove rocks. It removes one of the only known ways oxygen is produced in the deep ocean. We do not yet know how many creatures depend on that oxygen. We do not know what happens to the deep seafood chain if it disappears. We do not know what cascades through an ecosystem when you pull the foundation out from under it. And if the nodules are also tied into whatever larger system was producing those organized, shifting patterns, then the damage could go far beyond the loss of oxygen. Mining operations would not just be extracting resources. They would be tearing apart a system that has been running quietly for millions of years before anyone knew it was there. A system we do not understand, a system we cannot rebuild. Here is the part that terrifies Sweetman. Not just the loss, the irreversibility. Once you scrape the nodules off the seafloor, they do not grow back in our lifetime. They form at a rate of about 1 centimeter every million years. There is no putting them back. There is no fixing it later. The damage from a single mining run could last longer than the entire history of human civilization. And the scale of what is being planned is hard to picture. The machines designed for deep-sea mining are not delicate. They are massive, tank-like collectors built to drag along the seafloor and vacuum up nodules across enormous stretches of ground. A single mission could disturb hundreds of square kilometers. Multiple companies are preparing to run these operations at once. The Clarion-Clipperton Zone is huge, but so is the appetite for those metals. And here is the part that makes Sweetman uneasy. The decisions about whether to start full commercial mining are being made right now by a regulatory body called the International Seabed Authority. They are weighing applications, they are drafting rules. The window in which the world decides what happens to the deep Pacific is open today, not in some distant future. Sweetman and a growing number of his colleagues have been begging that body publicly to slow down, to wait, to let the science catch up with the ambition. Because once the machines start, there is no version of this story where we get to pause and find us out what we destroyed. And get this, more than 30 countries have now formally called for a pause on deep-sea mining until the science is better understood. The companies pushing for extraction have not. The pressure on the deep ocean is, in every sense, building from the surface down. The choice in front of us is uncomfortable. On one side, there is real, serious demand for the metals these nodules contain. The transition to cleaner energy depends on them. Modern technology depends on them. Saying no to deep-sea mining means finding those metals somewhere else, and there is no easy somewhere else. On the other side, there is a process happening at the bottom of the Pacific that may rewrite biology textbooks, a process that may help us understand life on other worlds, a process that has been running undisturbed since long before humans existed. The drone did not just give scientists new data, it gave us a problem, a real one, because for the first time, we know that the seafloor we were about to mine is not empty. It is doing something. It is making oxygen. It is moving. It is alive in a way we still do not fully understand. 5 kilometers below the Pacific, a process is running right now. It has been running for a very long time. The only reason we know about it is that one machine, looking at one patch of empty ocean floor, refused to move on. The question now is whether we will do the same, whether we will pause, focus, and look closer before we decide what happens next. And maybe the most uncomfortable part of this whole story is what it implies about the rest of the planet. If a system this strange, this active, this alive, was hiding under 5 kilometers of black water in a region we thought we already understood, what else is down there? How many other quiet processes are happening right now in places no human has ever looked? How many other things are waiting under our feet that by every rule we trust shouldn't exist? The drone answered one question. It opened 100 more, and every single one of them is a reason to be careful with what we do next. So, I want to hear from you. Do you think the world should slow down deep sea mining until we understand what is really down there? Or are the metals just too important to wait for? Drop your answer in the comments. I read them. And if this story changed the way you think about the ocean, hit subscribe, because we have more incredible discoveries coming in the weeks ahead. Until next time.